Tonight, we're exploring one of the strangest ideas in all of physics: the possibility that space itself may contain shortcuts. Wormholes have captured human imagination for a long time because the universe is so large that even our fastest machines barely begin to cross it. The deeper we look into space, the more clearly we see that ordinary travel runs into a quiet and overwhelming problem: distance. By the end of tonight, you'll understand why wormholes became such a powerful scientific idea, how they emerged from Einstein's theory of relativity, and why physicists still take them seriously, even though no one knows whether they truly exist. Space is so large that even our best machines barely begin to cross it. One of the fastest spacecraft human beings have ever sent into deep space is Voyager 1. It moves at a speed that sounds almost unbelievable when we compare it with anything on Earth. Yet the moment that speed is placed beside the distance to another star, it starts to feel small. If Voyager 1 were pointed toward the nearest star system beyond our own and kept moving at its present pace, the trip would take longer than recorded human history, many times over. It would take tens of thousands of years. That is the first quiet shock hiding inside this topic. Our machines can move fast, but the universe is larger than the word fast was ever meant to describe. Even light, the fastest thing we know, does not make the problem disappear. Light moves so quickly that it can circle Earth many times in a single second. It can cross the space between Earth and the Moon in a little over 1 second. By ordinary standards, that feels almost instant. But when light leaves our solar system and heads toward the nearest stars, even it needs years. The nearest star beyond the Sun is still more than 4 light years away. That means even light, which never seems to wait for anything, still spends more than 4 years crossing that gap. In space, speed is real, but distance keeps winning. This is what makes the universe feel different from the world our minds were built to understand. Human life is measured in days, seasons, and decades. Cities are measured in streets and hours of travel. Even large human projects are measured in years, maybe generations. But space stretches so far that these familiar units begin to lose their meaning. A journey to another star is not just a longer trip. It belongs to a different scale of reality. It asks for a level of patience that human civilization has never had to practice. It turns even the boldest plans into something that feels almost motionless. Once that feeling sinks in, a strange thought begins to make sense. Maybe the answer is not simply to go faster. Maybe the deeper problem is the path itself. That is where wormholes become so interesting. A wormhole is not appealing because it sounds magical. It is appealing because ordinary distance is such a brutal obstacle. Wormholes enter the conversation as a different kind of answer to the same old problem. Instead of asking how to make a ship cross a huge distance faster, the idea asks whether the distance itself could be bypassed. Could space-time have a shorter route hidden within it? Could two places that look extremely far apart from the outside be connected by a much shorter path underneath the surface of ordinary space? This is why wormholes are so often linked to faster-than-light travel, even though the idea is more subtle than that phrase suggests. The traveler inside the wormhole would not necessarily be locally breaking the speed limit of nature. The traveler would not need to outrun light in the normal sense. The shortcut comes from geometry. If two faraway regions are connected by a shorter inner route, then the journey could appear faster than light from the outside, without the traveler ever doing anything forbidden in their own immediate surroundings. In other words, the trick is not extra speed. The trick is a shorter path. That idea may sound like pure imagination at first, but it did not come from fiction alone. It came from the same theory that changed our understanding of gravity. Einstein's general theory of relativity showed that space and time are not fixed, empty containers. They can bend, they can curve. Matter and energy shape the geometry around them. Planets move the way they do because they follow the curved structure of spacetime. Light also follows that curvature. Once physics opened that door, the universe became stranger and richer than it had seemed before. Space was no longer just a blank stage. It had shape. It had structure. And once that became true, the possibility of unusual pathways began to appear in the mathematics. That does not mean wormholes are known to exist. It does not mean the universe is filled with hidden tunnels waiting to be found. It simply means the question became serious enough for physics to ask. Einstein's equations allow strange geometries, and among those strange geometries are bridge-like possibilities that later came to be associated with wormholes. That is one reason the topic has never gone away. It stands in a rare place between real science and deep speculation. It is grounded enough to be studied, but uncertain enough to remain mysterious. In recent years, the subject became even more intriguing. Physicists found ways to explore wormhole-like behavior in carefully designed quantum systems. These were not real tunnels opening in a laboratory, and they were not machines for travel. But they mattered because they showed that wormhole ideas can be tested in limited and indirect ways. The topic is still deeply theoretical, yet it is no longer trapped only in old thought experiments. It has become part of a living scientific conversation. So this is the quiet reason wormholes matter. Space is unimaginably large. Ordinary travel runs into the wall of time. Even light begins to feel slow when the universe is measured in years, centuries, and ages. Wormholes remain fascinating because they offer a different question altogether. If the universe is shaped by geometry, then perhaps the greatest barrier in space is not speed, but distance itself. And if distance is part of geometry, then maybe geometry can, under the right conditions, contain a hidden door. A wormhole is one of the strangest ideas in physics because it sounds like fantasy, yet it grows out of real equations. The simplest way to describe it is this: a wormhole is a possible shortcut through spacetime. Two places that look very far apart from the outside could, in theory, be linked by a shorter path underneath the ordinary layout of space. That is the basic picture. The full physics is deeper than that, but this gives the mind something clear to hold. The key word here is geometry. A wormhole is not mainly about engines, fuel, or pushing a ship harder through empty space. It is about the shape of space and time themselves. In everyday life, we imagine space as a flat, open stage where objects move from one point to another in a simple line. General relativity gave a different picture. It showed that space and time can bend, curve, and take on structure. Once that became part of physics, it opened the door to much stranger possibilities. A wormhole is one of those possibilities. A useful image is a sheet of paper. Imagine drawing two dots on that paper, one on the left side and one on the right. If the paper stays flat, the shortest path is a line across the surface. But if the paper is folded so the two dots come close together, a new route appears. A tunnel through the fold would connect them much more quickly than the long route across the surface. That picture helps explain why wormholes are so fascinating. They suggest that the universe may contain hidden shortcuts built into geometry itself. There is another image that works well too. Think about an ant walking across a curved leaf. From the ant's point of view, the world is the surface it can walk on. The route may look long if the ant has to stay on that surface. But if the leaf bends in a way that brings two places close together, the shape of the leaf changes the path. In a similar way, a wormhole is a claim about the shape of spacetime, not a claim that travelers simply found a stronger engine. These images are helpful, but they are still only images. A wormhole is not literally a tunnel drilled through folded paper. It is a mathematical idea about curved spacetime. That matters because the paper image can make wormholes feel too solid and too simple. In actual theory, a wormhole would be a region where spacetime is connected in an unusual way. The inner route would be shorter than the ordinary route outside. That is the real heart of the idea. Another important part of the definition is the word hypothetical. Physics can describe wormholes, but description is not the same thing as proof of existence. A map can show a path through a forest, yet that does not mean the path is easy to walk, safe to cross, or even truly open. In the same way, Einstein's equations can allow spacetime shapes that behave like wormholes. But nature still has to decide whether such shapes can really form, survive, and remain open. That uncertainty is one reason wormholes remain so compelling. They live in the space between mathematics and reality. This is also why wormholes attract so much attention in both science and fiction. They offer a simple dream in a universe ruled by enormous distance. They suggest that remoteness may sometimes be a feature of the map, not a permanent barrier in the landscape itself. They give shape to the hope that the universe may contain routes we do not yet know how to use. So for now, the clearest way to carry the idea forward is this. A wormhole is a hypothetical shortcut through spacetime, a hidden path created by geometry rather than speed. And once that possibility appears, the next question rises naturally. If space and time can curve enough to allow something like this, what else do Einstein's equations allow? To understand why wormholes became a serious idea in physics, we have to step back and look at the theory that made them possible. That theory is general relativity. Before Einstein, many people imagined space as a kind of empty stage. Objects moved across it. Time passed in the background. Gravity pulled things together like an invisible force reaching across that stage. It was a useful picture, and it worked well for many everyday situations. But Einstein found that the deeper picture was stranger and more beautiful. In general relativity, space and time are woven together into one structure, spacetime. This spacetime is not stiff or fixed. It can bend, it can stretch, it can curve. Matter and energy tell spacetime how to bend, and curved spacetime tells matter how to move. That is one of the most important ideas in modern physics. Gravity is no longer just a hidden pull between objects. It becomes the shape of the path itself. A simple way to picture this is to imagine rolling a ball across a flat floor. On a flat surface, the ball moves in a straight line unless something pushes it. Now imagine the floor is curved downward in the middle, like a smooth bowl. The ball still tries to move naturally, but now its path bends because the surface itself is shaped differently. In a loose way, that is how general relativity asks us to think. Planets are not being yanked through empty space by invisible strings. They are moving along paths shaped by curved spacetime. This idea changed everything. It explained the orbit of Mercury more accurately than older theories had. It predicted that light would bend around massive objects. It predicted black holes long before they were widely accepted. It even predicted that time itself runs differently in strong gravity. The theory was powerful because it did more than describe gravity. It replaced the old stage entirely. Once space-time became something flexible and physical, the universe became capable of much stranger shapes than people had once imagined. That is where wormholes begin to enter the story. Einstein's equations do not describe only one possible kind of universe. They allow many possible geometries, depending on how matter, energy, and curvature are arranged. Some of those solutions look familiar, like the space-time around a planet or star. Others are more extreme, like the geometry around a black hole. And some are so unusual that they seem almost unreal at first glance. Wormhole-like structures appear in this more unusual part of the theory. This is an important point, because it means wormholes were not invented by science fiction writers and then borrowed by physics later. The idea rose from the mathematics of relativity itself. Once physics accepted that space and time could curve, connect, and behave in unfamiliar ways, the possibility of bridge-like structures became worth studying. The equations opened the door first. Imagination followed after. Still, it is important to stay calm and careful here. When physicists say the equations allow something, that does not mean nature must build it. Mathematics can show that a structure is possible within a theory, but the real universe may still place limits on whether that structure can form, remain stable, or be used. A map may contain a road through the mountains, but the road could be blocked, broken, or too dangerous to cross. In the same way, relativity can point towards strange shapes in space-time without promising that they exist in a friendly or useful form. That tension is part of what makes wormholes so fascinating. They are not pure fantasy. They are rooted in one of the greatest scientific theories ever written. But they are also not established objects like stars or planets. They live in a middle space. The theory invites them in, while reality keeps asking harder questions. Can such a structure form? Could it stay open? Could anything pass through it? Could the laws of physics allow that kind of journey without collapse or paradox? General relativity also changes the way we think about distance itself. In everyday life, distance feels simple. Two places are separated by so many meters or kilometers. But in curved space-time, distance can become more subtle. The shortest path between 2 points depends on the shape of the space between them. Once the shape changes, the meaning of near and far can change too. That is the deeper reason wormholes matter. They are not just strange tunnels placed into an ordinary universe. They are a reminder that in Einstein's picture, the universe may be shaped in ways that make ordinary distance less absolute than it seems. This gives us the foundation we need. Gravity is curvature. Space-time is flexible. Einstein's equations allow more than one shape for reality. And among those possible shapes are bridge-like ideas that later grew into the wormhole concept. In the next section, we can move from this broad foundation into the first famous version of that idea. This gives us the foundation we need. Gravity is curvature. Space-time is flexible. Einstein's equations allow more than one shape for reality. And among those possible shapes are bridge-like ideas that later grew into the wormhole concept. In the next section, we can move from this broad foundation into the first famous version of that idea, the Einstein Rosen bridge. Once general relativity opened the door to strange shapes in spacetime, physicists began exploring what those shapes might look like. One of the earliest and most famous ideas connected to wormholes came from Albert Einstein and Nathan Rosen in 1935. Their work introduced what later became known as the Einstein Rosen bridge. This is an important moment in the history of the topic because it gave physics one of its first true bridge-like structures in spacetime. At the same time, it is also where a lot of confusion begins, because the original bridge was not the same thing as the stable travel tunnel that people often imagine today. Einstein and Rosen were working through deep problems in relativity. One of the big issues involved singularities, places where the equations seem to break down or produce infinities. These were troubling because they suggested that the theory might be pointing toward regions where ordinary understanding failed. Einstein was often uncomfortable with that kind of result. He hoped that a deeper or cleaner interpretation of the equations might avoid at least some of these troubling features. In this setting, he and Rosen explored a mathematical structure that looked like two regions of spacetime connected through a kind of bridge. The bridge appeared when looking at a particular description of a black hole geometry. In a simplified picture, it seemed as though two separate regions could be joined together by an inner connection. This was a striking idea. It suggested that spacetime might be able to connect distant domains through a hidden link. Later generations looked back at this bridge and saw in it the early shape of what would become the wormhole concept. But the original Einstein-Rosen bridge had a major problem. It was not a stable passage that a traveler could simply enter and cross. It closed too quickly. In practical terms, the bridge pinched off before anything could move through it from one side to the other. This is one of the most important points to understand. The bridge existed as a mathematical feature of the spacetime geometry, but it did not function like a doorway held open for travel. It was more like a fleeting connection than a usable road. That difference matters because popular imagination often turns the Einstein-Rosen bridge into something more friendly than it really was. In movies or casual conversation, people often picture it as a cosmic tunnel with one opening here and another opening somewhere far away, stable enough for a ship to pass through. But the original bridge did not give physics that kind of object. It gave something more delicate and more limited. It showed that relativity could produce bridge-like structures, but it did not solve the much harder problem of making such a structure traversable. Another reason this section matters is that it helps separate historical origin from later development. The Einstein-Rosen bridge was an early clue. It showed that spacetime could behave in ways that ordinary intuition never expected. But the fully developed idea of a wormhole that humans, signals, or spacecraft might cross came later. Later, physicists had to ask a new question. What would it take to keep a bridge open long enough for passage? That question moved the subject from mathematical curiosity toward the modern idea of a traversable wormhole. It is also worth noticing how closely the bridge was tied to black hole mathematics. This helped shape the public image of wormholes for decades. People began linking black holes and wormholes in the same breath, almost as if one naturally led to the other. There is a reason for that connection. both ideas grow from extreme solutions in general relativity. Both involve deep curvature and unusual spacetime structure, but they are still different ideas. A black hole is an object we now have strong evidence for. A wormhole remains hypothetical. And the Einstein Rosen bridge, while historically important, did not prove that black holes are secret tunnels waiting to be used. So the real importance of the Einstein Rosen bridge is quieter than the myth around it. It did not hand us an interstellar shortcut. It did something more foundational. It showed that relativity was strange enough to allow bridge-like geometry at all. It made the wormhole idea scientifically serious enough to keep studying. It gave later physicists a place to begin, even though the road ahead remained difficult. That is why this section sits at such an important point in the story. First, we learned that spacetime can curve. Then, we saw one of the earliest cases where that curvature seemed to connect separate regions through a bridge. Now the next step becomes natural. If the original bridge was too unstable to cross, what would a truly usable wormhole need in order to stay open? The Einstein Rosen bridge showed that general relativity could produce something that looked like a connection between separate regions of spacetime. But it also showed a major limitation. A bridge can appear in the mathematics without becoming a usable passage. If it closes too quickly, then nothing can cross it. That problem pushed physicists toward a more practical question. If a wormhole were ever to matter for travel, communication, or exploration, what would it actually need to be like? That is where the idea of a traversable wormhole becomes important. A traversable wormhole is a wormhole that stays open long enough for something to move through it. That something could be a beam of light, a signal, or in the most dramatic version of the idea, a person or spacecraft. The word traversable is doing a lot of work here. It does not just mean that a tunnel exists. It means the tunnel remains open, connected, and physically gentle enough to cross without instantly crushing or trapping whatever enters it. This version of the concept became especially clear in the late 1980s through work by Michael Morris and Kip Thorne, along with other physicists thinking carefully about the geometry of wormholes. Their goal was not to claim that wormholes had been found in nature. Instead, they asked a controlled question inside the language of relativity. If you wanted a wormhole that could actually be crossed, what conditions would the equations require? That shift was important because it moved the subject away from a collapsing bridge and toward a more detailed blueprint of what a usable wormhole would have to look like. One of the central features in that blueprint is the throat. The throat is the narrow inner region that connects one mouth of the wormhole to the other. If this throat pinches shut too quickly, travel becomes impossible. So a traversable wormhole must have a throat that remains open long enough for passage. That may sound simple at first, but it changes everything. A stable opening means the geometry cannot behave like the original Einstein Rosen bridge, which closes before any traveler could use it. The tunnel must resist collapse. A second requirement is that the wormhole must not contain an event horizon in the ordinary one-way sense associated with black holes. If one mouth behaved like a point of no return, then entering it would not amount to travel in the useful sense people imagine. A traversable wormhole has to allow entry and exit. It has to function more like a passage than a trap. That is one reason the popular habit of blending black holes and wormholes together can become misleading. A usable wormhole has very different needs from an object that swallows everything crossing a boundary. A third requirement involves tidal forces. Gravity does not only pull, it can also stretch and squeeze. Near very massive objects, the difference in gravitational pull from one part of a body to another can become extreme. For a wormhole to be traversable in any practical sense, these tidal forces would have to stay mild enough that a traveler is not torn apart. This makes the concept feel much less like a glowing portal from fiction, and much more like an engineering problem written into the fabric of spacetime itself. The route must exist, remain open, and be physically survivable. A fourth requirement is time. A usable wormhole has to stay calm enough for passage over some meaningful interval. Even if the opening exists for only a tiny instant, that may not help anything macroscopic cross it. Signals, particles, or travelers need a structure that persists. Stability is part of traversability. Geometry alone is not enough if the geometry vanishes before anything can use it. Once physicists began asking for all these conditions at once, the problem became much harder. A traversable wormhole was no longer just an elegant shape in an equation. It became a demanding physical object with strict requirements. It needed an open throat, no destructive horizon, manageable tidal forces, and enough stability for crossing. And when theorists tried to satisfy all of those demands, they kept running into the same obstacle. Ordinary matter did not seem able to hold such a structure open. The equations pointed towards something stranger. That is one reason traversable wormholes are so fascinating. They feel like a threshold between two worlds of thought. On one side is pure mathematical possibility. On the other side is physical reality, with all its harsh demands. Traversable wormholes sit right on that boundary. They show how far relativity can stretch the imagination, while still forcing every hopeful idea to answer to stability, structure, and survival. So this version of the wormhole idea is much more specific than the broad image people often carry. It is not just a tunnel between distant stars. It is a tunnel that must remain open, permit two-way passage, avoid deadly internal forces, and survive long enough to matter. Once the idea becomes that concrete, the beautiful image of a shortcut starts to reveal its true cost. Once a wormhole is imagined as a real passage instead of a beautiful shape in an equation, the hardest part of the idea begins to appear. A traversable wormhole must stay open. Its throat cannot simply collapse the moment anything tries to pass through. That sounds simple when spoken aloud, but in physics, it creates one of the biggest obstacles in the whole subject. The equations seem to point toward a very strange requirement. Ordinary matter does not appear to be enough. Something more unusual may be needed to hold the geometry open against its natural tendency to pinch shut. This is where the phrases exotic matter and negative energy begin to enter the story. These phrases can sound dramatic, almost like science fiction, but their role in the theory is more precise than that. They are not names for a magical substance. They describe unusual stress and energy conditions that seem able, at least on paper, to support a traversable wormhole. In ordinary situations, matter and energy tend to curve spacetime in ways that pull inward. They help create collapse, attraction, and concentration. A wormhole seems to need something that can, in a sense, push the other way. It needs a form of stress energy that resists the throat from closing. That is why this kind of matter is called exotic. It behaves differently from the familiar matter that makes up stars, planets, gas clouds, and living bodies. In the wormhole picture, the geometry must be supported by something that does not act like normal material. Instead of helping gravity narrow the passage, it would help preserve the opening. In simple terms, it plays the role of space-time scaffolding. It does not build the tunnel like bricks build a wall. It helps stop the tunnel from collapsing under its own geometry. The phrase negative energy is often used here because certain wormhole models seem to require energy conditions that fall below what ordinary matter usually allows. In daily life, energy is something we imagine as positive. Heat adds energy, motion carries energy. Light brings energy. But in some parts of theoretical physics, especially in quantum settings, there are situations where energy can behave in more subtle ways. In those settings, physicists can talk about regions whose energy is lower than a chosen reference level, or about effects that act like negative energy in a limited sense. These ideas are not fantasy, but they are delicate, tightly constrained, and far removed from the kind of bulk material a wormhole would seem to need. One of the most famous examples is the Casimir effect. This effect appears when two very closely spaced metal plates change the behavior of the quantum vacuum between them. The empty space between the plates is not truly empty in the simplest sense. Quantum theory allows fluctuating fields even in a vacuum. Under the right conditions, the arrangement of those fluctuations changes, and this can create a measurable force pushing the plates together. The Casimir effect matters in this discussion because it shows that vacuum conditions can become physically real. Empty space is not as blank as it seems. Quantum fields can shape what happens there. That is why the Casimir effect is mentioned so often in conversations about wormholes. It gives a real example of strange vacuum behavior and of energy conditions that differ from everyday intuition. It proves that the quantum vacuum can do surprising things. It shows that nature is capable of more subtle behavior than classical pictures would suggest. This matters because wormholes seem to need exactly that kind of subtlety. They need the laws of physics to permit something more flexible than ordinary matter and ordinary empty space. But this is also where caution becomes necessary. The Casimir effect does not hand us a wormhole building material. It does not mean physicists have found a usable source of negative energy large enough to hold open a tunnel across space. The effect is tiny. It appears only under very special conditions. It is hard to produce, hard to control, and deeply limited in scale. That difference matters. A small quantum vacuum effect in a laboratory is one thing. A stable passage through space-time large enough for travel is something vastly more demanding. So the wormhole idea begins to change here. It still remains mathematically fascinating, but the physical cost becomes much clearer. A traversable wormhole seems to ask for a kind of support that ordinary matter cannot provide. Theory hints at strange possibilities in the quantum world, and the vacuum itself is richer than it first appears. But the distance between these delicate effects and a true travel tunnel is enormous. The closer wormholes get to becoming real objects, the more fragile and difficult they begin to seem. A wormhole can sound simple when it is first imagined. Two distant places are linked. A traveler enters one side and comes out the other. The picture feels clean, almost effortless. But the deeper the idea is examined, the more delicate it becomes. A wormhole is not like a tunnel carved through rock, where solid walls hold their shape. It is a structure made from spacetime itself. That makes it far more fragile. The same geometry that allows a shortcut may also be eager to destroy it. The main problem is the throat, the narrow connecting region between the two mouths. For travel to be possible, that throat must stay open. If it pinches shut too quickly, then no signal, no particle, and no traveler can make it across. In many models, this is exactly what happens. The wormhole does not remain a calm passage. It behaves more like a brief and unstable fold in space-time, one that naturally wants to collapse under its own gravitational structure. This is part of what makes wormholes so different from ordinary objects. A bridge on Earth can stay standing because steel, stone, or concrete support it. A cave can remain open because the surrounding rock holds its shape. But a wormhole is not built inside space. It is built out of space. Its stability depends on the curvature itself. If that curvature is not supported in just the right way, the geometry closes in on itself. The passage disappears before it can serve any purpose. Even if a wormhole could briefly exist, the problem would not end there. Matter passing through it may disturb the structure. A wormhole that looks stable in a clean equation may become less stable the moment anything enters the throat. A beam of light carries energy. A particle carries energy. A spacecraft certainly would. That added energy can change the curvature of spacetime around the passage. In other words, the very act of using a wormhole may help destroy it. Radiation can create similar trouble. Space is not perfectly quiet. Fields fluctuate. Particles and waves move through the universe. Near an already delicate structure, even small disturbances may matter. A wormhole may have to remain balanced under conditions that are difficult to maintain. Tiny shifts could become large problems. This gives the whole idea a very different feeling from the smooth portals of fiction. A real wormhole, if one could exist at all, would likely be less like an open door and more like a balancing act at the edge of collapse. Time is part of the difficulty too. A passage is only useful if it stays open long enough for something to cross. If a wormhole survives for only a tiny instant, that may not be enough. Signals need time. Travelers need time. Stability is not just about existing. It is about lasting. A route that closes before anything can pass through may still be mathematically interesting, but it is not a usable path across the universe. This fragility is one reason exotic matter becomes so important in wormhole theory. Without some unusual support, the throat seems to narrow and close. Yet even with that support added in theory, there is no guarantee the structure would remain calm once real disturbances begin. A wormhole must resist gravity, resist collapse, survive passing matter, and remain open long enough to matter. Each one of those demands is difficult. Taken together, they make the problem feel severe. So the image of a wormhole begins to change as the physics becomes clearer. At first, it appears as a graceful shortcut. Then it begins to look more like a fleeting crack in geometry, something that might collapse the moment the universe presses against it. The beauty of the idea remains, but it becomes a far more delicate beauty. A wormhole is no longer just a doorway between distant stars. It is a structure that must survive its own existence, survive disturbance, and somehow remain open, against a very strong tendency to close. Once that fragility becomes clear, the scale of the challenge starts to feel much larger. Once wormholes begin to look fragile, the next question becomes unavoidable. If a wormhole is going to stay open, what kind of energy would that actually require? This is where the idea begins to feel much heavier. The difficulty is no longer only about finding the right shape in an equation. It becomes a question of scale. Even if the laws of physics allow a traversable wormhole in principle, the amount and arrangement of energy needed to support one may be far beyond anything human beings can realistically approach. Part of the problem comes from the strange kind of support a wormhole seems to need. It is not enough to pour ordinary energy into the system the way an engine burns fuel. A wormhole throat appears to require very unusual stress and energy conditions. The geometry must be held open in a way that resists collapse instead of feeding it. This means the issue is not only how much energy is needed, but what kind of energy distribution is needed. The pattern matters as much as the total amount. That makes the subject hard to picture, because most large human projects involve familiar energy use. A rocket uses stored chemical energy. A star shines by nuclear fusion. A city runs on electricity carried through wires and machines. Those examples make energy feel like something that can be gathered, stored, and spent. A wormhole seems to ask for something stranger. The support must be built into spacetime itself. It must shape curvature, preserve an opening, and prevent the throat from collapsing. That is a very different kind of demand from simply moving an object from one place to another. When physicists talk about wormholes, the numbers involved can become enormous very quickly. Different models lead to different estimates, and that uncertainty matters. But the overall picture stays the same. The scale often rises far beyond familiar engineering. In some descriptions, the required energy becomes comparable to the mass energy of planets, stars, or other immense cosmic systems. In others, the exact quantity changes, but the basic lesson does not. A traversable wormhole is not a machine that merely stretches present technology. It belongs to a level of space-time engineering that feels almost like trying to shape part of the universe itself. Quantum theory does offer a small opening into this conversation, because it allows unusual energy behavior under limited conditions. But those strange states are tightly constrained. They do not appear as unlimited tools waiting to be harvested. They appear as delicate effects under very particular circumstances. That creates a tension at the heart of the wormhole idea. The mathematics points toward what might be needed, and the quantum world hints that nature is capable of subtle surprises. Yet everything known so far suggests those effects are tiny, brief, or difficult to control. The path from that kind of subtle quantum behavior to a stable passage across space remains unimaginably large. This is why wormholes begin to feel less like advanced vehicles and more like cosmic infrastructure. A ship can be built, fueled, repaired, and launched. A wormhole, if it were ever possible, would have to be created or stabilized as part of the fabric of spacetime itself. It would not simply carry energy, it would be shaped by energy. That makes the whole idea feel closer to moving mountains with geometry than to building a faster spacecraft. The challenge is not just motion. It is structure on a scale that human industry has never touched. No known technology comes close to doing this. Humanity can send probes across the solar system. It can split atoms. It can detect black holes and gravitational waves. These are extraordinary achievements. Yet they remain tiny compared with the idea of holding open a throat in spacetime using exotic energy conditions. The gap is so large that it changes the emotional feeling of the subject. Wormholes stop feeling like a hidden invention that just has not been built yet. They begin to feel like something that may belong to a much deeper level of physical reality than our tools can presently reach. That does not make the idea meaningless. In some ways, it makes it more interesting. A theory becomes especially powerful when it shows how large the universe still is, not only in distance, but in possibility. Wormholes force physics to ask what spacetime can endure, what energy can do, and whether geometry itself can ever be engineered at all. They take a simple dream of travel and stretch it into a question about the structure of reality. And once the problem grows that large, another strangeness begins to enter the picture. If a wormhole can change the path through space, then under some conditions it may also begin to change the path through time. A wormhole begins as an idea about distance. It offers a shortcut through space-time, a way for two far-apart places to become connected by a shorter inner path. But once the idea is studied more closely, something even stranger appears. A shortcut through space may also become a shortcut through time. The geometry does not only shape where things go, it also affects when they arrive. That is where the wormhole story becomes much deeper than simple travel. This grows out of one of the central lessons of relativity. Time is not separate from space. It is woven into the same structure. Motion affects time. Gravity affects time. Clocks do not always agree when they have lived through different conditions. A clock moving very fast can tick differently from one that stays still. A clock deep in a strong gravitational field can tick differently from one far away. These are not illusions. They are real features of space-time. That means a wormhole, if it truly links two regions of space-time, may also link two different time conditions. Imagine that a wormhole has two mouths, one here and one somewhere else. At first, the clocks at both mouths may agree. But if one mouth is moved at very high speed and then brought back, or if one mouth spends time in a much stronger gravitational field, the two mouths may no longer share the same history of time. This is similar to the logic behind the famous twin paradox in relativity. Two clocks begin together, live through different journeys, and then no longer agree when compared. If a wormhole keeps the two mouths connected internally, while their outer histories drift apart, something very strange can happen. The wormhole may connect not only two different places, but also two different moments. That is the heart of the time travel problem. A person could, in principle, enter one mouth of the wormhole and exit the other at a time that does not match the ordinary outside route. Depending on how the mouths were moved and how their clocks shifted, the exit could lie in the future relative to one side, or even in the past relative to the outside world. The wormhole would no longer be just a passage through space. It would become a passage through time as well. This does not mean every wormhole becomes a time machine. The point is more specific. Under certain conditions, relativity seems to allow the possibility. That is why wormholes are often treated with such caution in physics. They do not merely raise engineering questions. They raise questions about causality, the deep rule that causes come before effects. Once a wormhole can connect different times, it starts pressing against the ordinary order of events. That is where the famous paradoxes enter the picture. If a traveler could go backward in time through a wormhole, could they interfere with events that led to their own journey? Could an effect arrive before its cause? could information appear in a loop with no clear beginning? These are not just playful puzzles. They point toward a real tension between relativity, geometry, and the basic logic by which the universe seems to operate. Physics is built on patterns, predictions, and cause leading to effect. Time travel wormholes seem to threaten that order. The idea becomes even stranger when imagined as a closed loop. A traveler might leave one mouth, emerge in the past, move through ordinary space, and then arrive back at the original starting point before they had left. In principle, such loops are called closed time-like curves. The name is technical, but the idea is simple enough. It is a path through space-time that curves back into its own past. A wormhole, under the right conditions, may allow such a path to exist. This is one reason the wormhole idea never stays confined to travel alone. The moment the geometry becomes rich enough to shorten distance, it begins to touch deeper questions about time itself. Space travel starts to blend into time travel, and the whole subject takes on a more fragile and dangerous feeling. A tunnel across the stars sounds daring. A tunnel that may disrupt the order of cause and effect sounds far more serious. So wormholes occupy a very unusual place in physics. They begin as a response to distance, but they quickly force a confrontation with time. They suggest that the fabric of reality may be flexible enough to connect different places by hidden routes. Yet that same flexibility may also allow clocks to drift apart, histories to separate, and pathways to loop back on themselves. The universe begins to feel less like a simple timeline and more like a landscape whose deeper roots may not respect ordinary order. Once that possibility appears, a harder question rises above all the others. If wormholes can become time machines in principle, does nature somehow prevent them from ever truly working? Once wormholes begin to touch time travel, the subject changes. The question is no longer only whether a shortcut through space can exist. The deeper question becomes whether the universe would permit that shortcut to disrupt the order of cause and effect. Physics depends on that order. A cause happens, then an effect follows. A star explodes and light travels outward. A person makes a choice, and then the result appears. If wormholes could be used to move into the past, that chain might begin to twist back on itself. That is why many physicists became uneasy about time-traveling wormholes, even if the equations seemed to allow them in principle. One of the best-known responses to this problem came from Stephen Hawking. He suggested that the laws of physics may protect the universe from these kinds of paradoxes. This idea became known as chronology protection. The name sounds formal, but the meaning is simple. Chronology is the order of events through time. Chronology protection is the idea that nature may prevent situations where that order breaks down in dangerous ways. In this view, the universe may allow strange mathematical possibilities while still refusing to let them become real-time machines. The reason for this concern is easy to understand. If a wormhole connects different times as well as different places, then it may allow a traveler or even a signal to arrive before it was sent by the ordinary outside route. That opens the door to paradoxes. A message could warn someone before they choose to send it. An event could become the cause of itself. Information might loop through time with no clear beginning. These problems are not just odd thought experiments. They suggest that prediction itself could start to fail. If cause and effect are no longer stable, then the logic that physics depends on may begin to weaken. Hawking's idea was that the universe may stop this from happening before a full time machine ever forms. In some calculations, quantum effects appear to grow stronger. Near the boundary where closed time loops would begin, radiation may pile up. Energy may become unstable. The region may grow violently disturbed before anything can actually pass through in a way that breaks chronology. In simple terms, the closer a wormhole gets to functioning like a time machine, the more the laws of physics may push back. This does not mean the matter is fully settled. Chronology protection is a powerful idea, but it is not a final proven law in the same way as something directly confirmed in everyday experiment. The deeper problem is that the argument sits at the meeting point of general relativity and quantum physics. Relativity describes gravity and spacetime on large scales. Quantum theory describes the strange behavior of matter and fields on very small scales. A true answer about time-traveling wormholes may require a full theory of quantum gravity, and physics still does not have a complete one. That leaves the subject open, but only in a careful sense. The door is not fully closed, yet it is surrounded by warning signs. There is also a more subtle reason this idea matters. Chronology protection suggests that mathematics alone may not tell the whole story. A space-time geometry can look possible inside an equation, yet the full universe may contain deeper rules that keep reality coherent. This is part of the beauty of physics. The equations invite bold possibilities, then nature tests them through stability, energy, and consistency. Wormholes may be one of the clearest examples of this tension. They seem to stand right at the edge, where elegant geometry meets the need for a universe that still makes sense. So the subject becomes more reflective here. Wormholes are no longer only about distant stars or hidden routes across the cosmos. They begin to press on the meaning of time itself. If a wormhole could become a bridge into the past, then the universe would need some way to handle that possibility. Hawking's answer was that perhaps it does. Perhaps reality protects its own timeline, not by forbidding strange mathematics, but by making those dangerous structures unstable before they can fully form. That idea leaves wormholes in a fascinating position. They remain serious enough to study, strange enough to challenge intuition, and limited enough to remind us that the universe may defend its own order. The geometry may allow more than ordinary experience suggests, yet nature may still guard the sequence of events with great care. And once that tension becomes clear, attention begins to move away from giant tunnels and toward the smallest scales of all, where space-time itself may flicker with hidden structure. So far, wormholes have been imagined as large structures, big enough to connect distant regions of space and perhaps even allow travel. But there is another way the idea can appear in physics. Instead of thinking on the scale of stars and spacecraft, some physicists have wondered what space-time may look like at the very smallest scales imaginable. And at that scale, space-time may stop feeling smooth and quiet. It may become restless. In everyday life, space seems calm and continuous. A room looks steady. The sky looks open. Even the emptiness between stars can feel like a silent background waiting to be crossed. But quantum physics has taught us that the world becomes far stranger as we look deeper. At very small scales, empty space is not truly empty in the simple sense. Fields fluctuate. Particles can briefly appear and disappear. The vacuum behaves less like nothing and more like a shifting sea of possibility. This led physicist John Wheeler to describe the smallest structure of spacetime with a vivid phrase, quantum foam. The image is helpful because it suggests motion, bubbling, and instability. A calm pond seen from far away may look flat, but up close, its surface can be full of ripples, bubbles, and constant movement. In a similar way, spacetime may look smooth from the scale of people, planets, and stars, while becoming rough and unsettled at scales far smaller than anything we can directly see. The scale involved here is almost beyond imagination. It is called the Planck scale, named after physicist Max Planck. This is a realm so tiny that ordinary ideas of distance begin to lose their usual meaning. At that scale, many physicists suspect that general relativity and quantum theory must meet in a deeper way than we currently understand. Space may no longer behave like a smooth geometric stage. Time may no longer flow in the clean way it seems to on larger scales. The fabric of reality itself may become grainy, fluctuating, or topologically strange. That is where tiny wormholes enter the picture. Some speculative ideas suggest that microscopic wormholes might briefly appear and vanish inside this quantum foam. These would not be stable tunnels waiting for travelers. They would be fleeting features, smaller than anything a human being could ever cross. They would come and go on timescales so short that they would belong to the deepest hidden layer of nature. In this picture, wormholes would not first appear as giant roads through the cosmos. They would begin as tiny, momentary wrinkles in the quantum structure of spacetime. This is a very different mood from the image of a large, traversable passage between stars. It makes wormholes feel less like grand cosmic architecture and more like hidden turbulence at the bottom of reality. The idea is still speculative, and that must be said plainly. No one has observed these tiny wormholes directly. No experiment has revealed them as established features of nature. They remain part of a deeper attempt to imagine what spacetime may be doing, where current theories are incomplete. Still, the idea matters. It matters because it changes the question. Instead of asking only whether a civilization could one day build a wormhole, physics also asks whether wormhole-like structures may already belong to the hidden texture of the universe at a scale too small for ordinary experience. That makes the subject feel both smaller and larger at the same time. Smaller, because the structures being imagined are microscopic. Larger, because the question now reaches into the foundation of space and time themselves. There is also a very wide gap between tiny quantum wormholes and a human-sized tunnel. Even if nature does allow microscopic bridges in the foam of spacetime, that would not mean such structures could be enlarged, stabilized, or used for travel. The leap from a brief quantum feature to a safe passage across light years would be enormous. It would be like finding a ripple in water and then imagining it turned into a permanent bridge across an ocean. The comparison helps show just how different these two ideas really are. So the wormhole story becomes more subtle here. A wormhole may not only be a large bridge dreamed up for interstellar travel, it may also be a clue that spacetime itself is stranger than it appears from the human scale. At the deepest levels, the universe may not be smooth and empty at all. It may be restless, fluctuating, and full of hidden structure that briefly connects and disconnects in ways we do not yet fully understand. And once wormholes enter that quantum world, they begin to touch one of the most surprising ideas in modern physics, the possibility that geometry itself may be tied to quantum connection. As wormholes move deeper into modern physics, the idea begins to change shape again. At first, a wormhole sounds like a shortcut through space. Then it becomes a question about time, stability, and quantum structure. And in more recent theory, it begins to touch something even stranger: the possibility that space-time geometry and quantum connection may be linked at a very deep level. This idea became especially famous through work by Juan Maldacena and Leonard Susskind. They proposed a bold connection between two ideas that had once seemed very different. One idea was the wormhole, sometimes called an Einstein Rosen bridge. The other was quantum entanglement, one of the strangest features in all of physics. Entanglement describes a situation where two quantum systems become linked in such a way that their properties are connected, even when the systems are far apart. The proposal suggested that these two strange ideas might be related at a deeper level than anyone had expected. This became known through the phrase ER equals EPR. The letters refer to two famous pieces of physics history. ER stands for Einstein and Rosen, whose names are tied to the bridge-like spacetime structure. EPR refers to Einstein, Podolsky, and Rosen, who wrote a famous paper about the puzzles of quantum entanglement. The proposal does not mean the two ideas are identical in every simple sense. It means that under some conditions, the mathematics may hint that entangled systems and wormhole-like connections are different expressions of a deeper underlying structure. That possibility matters because it changes the way physicists think about both gravity and quantum theory. Instead of treating space-time as one thing and quantum information as another, the proposal suggests that geometry itself may grow out of patterns of connection. In that picture, the shape of space-time may not be the deepest layer of reality. It may emerge from relationships between more basic quantum ingredients. A wormhole, then, would no longer be only a tunnel through space. It could become a sign that connection and geometry are woven together. This is a beautiful idea, but it needs to be handled carefully. It does not mean that ordinary entangled particles become tiny portals that people can use for travel. It does not mean someone can entangle two objects and then step through a hidden tunnel between them. That is the kind of leap popular imagination often wants to make. But the theory is much more restrained. The wormholes involved in these discussions are not practical gateways. In many versions, they are non-traversable. They describe deep structure, not easy movement from one place to another. Even so, the idea had a major effect on theoretical physics. It helped reshape how many researchers think about the relation between gravity, quantum mechanics, and information. It suggested that space-time may be less like a fixed backdrop and more like something built from hidden patterns of quantum linkage. That is one reason the idea drew so much attention. It offered a possible bridge between two parts of physics that have long resisted unification. Gravity governs the large structure of the universe. Quantum theory governs the small. If entanglement and wormholes are related, then geometry itself may be one place where those two worlds meet. There is also something emotionally powerful about this idea. A wormhole seems like a bridge through distance. Entanglement seems like a bridge through quantum connection. Putting them together suggests that separation itself may be more subtle than it appears. Things that look far apart on the surface may be linked more deeply underneath. That does not make travel easy, but it does make the universe feel more interconnected than ordinary intuition would guess. This is part of why wormholes remain important, even when they seem too unstable or too demanding for real travel. They are not only possible roads across the cosmos, they are also clues about what spacetime may truly be. They invite physics to ask whether distance, geometry, and connection are all resting on deeper foundations. So the wormhole story grows more modern here. The question is no longer only whether a tunnel through spacetime can exist. The question becomes whether spacetime itself may arise from hidden quantum links. That possibility is still being explored, and much remains uncertain. But it has already done something important. It has turned wormholes from a strange corner of relativity into part of a much larger search for the underlying structure of reality. And once theory reaches that point, another question begins to follow naturally. If these deep connections are real in controlled mathematical settings, can any version of a traversable wormhole appear there too? For a long time, traversable wormholes seemed to belong almost entirely to speculation. The equations could describe them, but the conditions looked so severe that the whole idea felt distant from anything physically meaningful. Then modern theory introduced a more careful shift. Instead of asking whether a giant wormhole for spacecraft could be built, some physicists began asking a narrower question. In special mathematical settings, could a wormhole become traversable in a controlled and limited way? That change in approach mattered. It replaced the image of a dramatic tunnel across the galaxy with something much more modest and much more useful for theory. A traversable wormhole no longer had to mean a giant passage waiting for human travel. It could mean a small, highly idealized system where a signal might pass through a wormhole-like connection under very specific conditions. This made the subject feel less like fantasy and more like a laboratory for ideas. Some of the most important progress came from models built in highly controlled versions of spacetime used in theoretical physics. These settings are not copies of the real universe in all its complexity. They are simplified worlds where gravity, quantum fields, and geometry can be studied with greater precision. Within these controlled settings, theorists found that traversability can sometimes appear if the right ingredients are added. In other words, the wormhole does not stay open on its own, but under carefully arranged conditions it may briefly allow information to pass through. A central part of these models is the use of quantum effects and external couplings. Two sides of a system may be linked in a carefully tuned way, and that tuning can create the conditions needed for a wormhole-like passage to become traversable. This does not mean the wormhole becomes a wide tunnel with calm walls and empty space inside. It means the mathematics allows a message or disturbance to get through where it otherwise would not. The result is small, precise, and fragile, but it is still deeply important. It shows that traversability is not only a dream placed on top of relativity. Under the right theoretical conditions, it can emerge in a meaningful way. Negative energy remains part of the story here as well. The wormhole still needs something unusual to resist collapse. In these modern models, quantum effects can provide the right kind of behavior in a more controlled manner than older, broader wormhole ideas seem to allow. That does not remove the difficulty. It simply moves the conversation into a setting where the rules can be studied more carefully. The strange support the wormhole needs is still there, but it begins to look less like a vague fantasy and more like a specific requirement inside a well-defined mathematical system. This is why these models matter so much. They do not tell us that humanity is close to building a wormhole. They do not show that a tunnel across the stars is just waiting for better engineering. What they do show is that the boundary between impossible and possible may be more subtle than it first seemed. A wormhole can remain non-traversable in one setting and become traversable in another if the surrounding physics changes in the right way. That is a major conceptual step. At the same time, it is important to stay grounded. These models often live in mathematical worlds that are much cleaner and more controlled than the real universe. They are powerful tools for thought, but they are not blueprints for interstellar transport. Their value lies in what they teach about the relationship between gravity, quantum fields, information, and geometry. They are more like test chambers for deep ideas than design plans for future spacecraft. That makes this part of the wormhole story feel like real progress, but progress of a very special kind. It is progress in understanding, not progress in construction. It brings wormholes closer to the world of serious theoretical investigation, while still leaving them far from practical travel. It shows that the subject can be sharpened, refined, and explored with more discipline than the older popular image might suggest. So the picture becomes clearer here. Modern traversable models do not give us a doorway to another star system. They give physics something quieter and more valuable for now. They provide a controlled place to study how a wormhole-like passage might briefly work, how quantum effects can support it, and what that says about the deeper structure of spacetime. And once that becomes possible in theory, it becomes easier to understand one of the most misunderstood headlines in the whole subject: the claim that physicists created a wormhole on a quantum processor. By this point, the wormhole idea has already changed several times. It began as a strange possibility in relativity. Then it became a question about exotic matter, collapse, time loops, and quantum structure. Modern theory made the subject more precise by showing that limited forms of traversability could appear in controlled mathematical settings. That background is important because without it, one of the most famous recent wormhole headlines sounds far more dramatic than it really was. In 2022, a group of researchers carried out an experiment using a small quantum processor and a carefully chosen theoretical model. News stories quickly spread the idea that physicists had created a wormhole in a laboratory. That phrasing caught attention, but it also created confusion. No tunnel opened in space. No object vanished into one side and appeared out the other. No doorway through the universe was built. What the researchers did was subtler and, in its own way, more interesting. The experiment was designed to imitate the behavior of a wormhole-like system described in modern theory. The researchers used a simplified quantum model that had connections to ideas from gravity and spacetime geometry. In that model, information inserted on one side could behave in a way that matched what theorists would expect from a traversable wormhole in the mathematical description. The quantum processor was being used as a kind of physical stand-in, a machine capable of reproducing the logic of the equations in a limited and controlled form. That distinction matters. The experiment was not a wormhole in the ordinary sense. It was not a real bridge drilled into spacetime. It was a simulation of wormhole-related dynamics. In other words, the processor reproduced patterns of behavior that matched certain theoretical expectations. This is very different from opening an actual path through the cosmos. The value of the experiment came from its ability to test and explore ideas indirectly, not from building a literal tunnel. A useful comparison is a wind tunnel used in engineering. A wind tunnel does not contain the full sky. It does not recreate an entire storm system. But it can still teach researchers something real about how air flows around a wing. In a similar way, the quantum processor experiment did not contain an actual wormhole, but it gave physicists a controlled setting where certain wormhole-like behaviors could be studied. It was less like building a cosmic passage and more like creating a miniature stage where part of the theory could come alive. This matters because wormholes have long existed at the edge of what feels testable. They were often discussed as elegant but distant possibilities, trapped inside equations too extreme for experiment. The quantum processor story showed something new. Even if a real traversable wormhole remains far beyond present reach, some of the underlying ideas can be translated into systems that scientists can actually manipulate and observe. That makes the subject feel a little less remote. It brings wormhole theory closer to the world of experiment, even if only in a very narrow and carefully limited way. At the same time, trust depends on keeping the limits clear. The experiment did not prove that real wormholes exist in nature. It did not show that human beings are close to building one. It did not demonstrate travel through space-time. What it showed was that a quantum system could reproduce certain relationships that, in the theory, are described using wormhole language. That is a meaningful step in understanding, but it is not a shortcut to science fiction. Still, the experiment deserves attention because it reveals how theoretical physics often advances. A bold idea first appears in mathematics. Later, pieces of that idea become clear enough to test in simpler forms. The test is not the full thing itself, but it helps show that the theory has structure, discipline, and reach. The wormhole story on the quantum processor belongs to that tradition. It is not the construction of a tunnel. It is the study of a pattern. So the most honest way to hold this moment is with both caution and curiosity. The headlines were louder than the actual achievement, but the achievement was still real. Physicists did not open a door through space. They found a way to make part of wormhole theory experimentally approachable in a carefully designed quantum setting. That is quieter than the headline, but it is also more valuable. It shows that wormholes are no longer only distant ideas floating in thought experiments. Parts of the logic can now be explored with real machines. And once that is understood clearly, it becomes easier to return to the sky and ask a more familiar question. If wormholes are possible in theory, could any real object in the universe actually hide one? Few ideas in space capture the imagination like black holes. They are dark, extreme, and already feel like the edge of ordinary reality. So it is not surprising that people often connect them with wormholes. If black holes bend space-time more strongly than almost anything else in the universe, then it seems natural to wonder whether one of them might hide a tunnel inside. The image is powerful, a dark opening in space that does not end in destruction, but in passage. There is a reason this connection appears so often. Both black holes and wormholes come from the mathematics of general relativity. Both involve space-time behaving in ways far beyond everyday experience. Both are tied to intense curvature, strange horizons, and the possibility that geometry can become more exotic than it first seems. Historically, one of the earliest wormhole-like ideas, the Einstein Rosen bridge, was closely linked to black hole mathematics. That connection helped shape the public image of wormholes for generations. But the similarity can be misleading if it is pushed too far. A black hole and a traversable wormhole are not the same kind of object. A black hole is something astronomy now takes very seriously as a real feature of nature. We have strong evidence for black holes through their effects on nearby stars, hot gas, gravitational waves, and even direct imaging of the region around them. A traversable wormhole, by contrast, remains hypothetical. It appears in theory, but it has not been confirmed in the sky. The deepest difference is about what happens when something enters. A black hole is defined by an event horizon, a boundary beyond which escape is no longer possible in the usual sense. Once that boundary is crossed, the path inward continues. In ordinary black hole models, this does not lead to a calm tunnel that carries a traveler safely to another region of space. It leads deeper into extreme gravity. A traversable wormhole would need something very different. It would need a passage that stays open, avoids destructive collapse, and allows a traveler to emerge somewhere else. That is a much harder structure to maintain. Rotating black holes make the picture even more interesting. Some exact solutions in relativity suggest that under highly idealized conditions, rotating black holes may contain richer internal geometry than the simplest non-rotating case. This has encouraged some speculation that certain black hole-like objects could, in principle, be linked to wormhole structures. But these solutions are fragile, highly mathematical, and often depend on conditions that may not survive in the messy reality of the universe. Real black holes are not pristine diagrams. They form through collapse, interact with matter, and exist in environments full of disturbance. Then there is the problem of singularities and tidal forces. Near a black hole, gravity can become overwhelming. In some cases, the difference in gravitational pull from one part of an object to another can become extreme enough to tear it apart. Even if a mathematical solution seems to suggest a bridge-like route, that does not mean the route would be safe or even usable. The presence of a formal connection in the equations is not the same thing as a passage that living bodies, signals, or spacecraft could actually survive. This is why the popular image needs gentle correction. Falling into a black hole is not the same as stepping into a wormhole. One idea belongs to an object that appears to exist in nature. The other belongs to a very demanding kind of geometry that would need to resist collapse and allow passage. The overlap between them is part of the history of the subject, but the difference between them is part of the physics. Still, the question remains worth asking. Some wormhole models can resemble black holes from the outside. From a distance, both may bend light, affect nearby matter, and appear as compact regions of intense gravity. That means the universe could, in principle, contain objects that look black hole-like while hiding different internal structure. The trouble is that this possibility remains unproven. No observation has yet shown that a known black hole is actually a wormhole in disguise. So black holes sit beside wormholes in an interesting way. They help make the wormhole idea feel plausible because they prove that spacetime can become dramatically curved in the real universe. But they also remind us how hard nature can be. Extreme curvature does exist, yet it usually appears in forms that trap, crush, or hide, rather than gently connect. Wormholes may still be possible, but black holes alone do not give them to us. They only show that the universe is strange enough to keep the question alive. And once that becomes clear, the next challenge is no longer only theoretical. It becomes observational. If wormholes are out there, what would astronomers actually look for? So far, wormholes have lived mostly in theory. They appear in equations, in models, and in thought experiments about spacetime. But a deeper question remains. If wormholes exist in the real universe, how would anyone ever know? Astronomers cannot simply fly up to one and inspect it. They would have to search from far away using light, motion, gravity, and careful comparison. That makes the search both fascinating and extremely difficult. One important fact should come first. No telescope has confirmed a wormhole. No observation has shown, beyond serious doubt, that a real object in the sky is a wormhole. This matters because the idea is often discussed with such vivid imagery that it can start to feel almost established. It is not. Wormholes remain hypothetical. The search is real, but the evidence is not there yet. The difficulty begins with appearance. A wormhole, especially from far away, might not look dramatic in the way fiction suggests. It might not glow like a gateway or announce itself as a tunnel in the stars. In some models, a wormhole could look very similar to a black hole from the outside. Both could bend light strongly. Both could affect the paths of nearby stars or gas. Both could create regions where ordinary intuition begins to fail. That similarity is one reason the observational problem is so subtle. Even if a wormhole were present, it might hide behind the appearance of something more familiar. This is why gravitational lensing often enters the discussion. Gravity bends the path of light. Massive objects can distort the images of things behind them, almost like a glass lens bending what we see through it. Black holes can do this. Galaxies can do this. In principle, a wormhole might do it too, but the pattern may differ. Some theoretical models suggest that a wormhole could create unusual image distortions, duplicate light paths, or other features that do not perfectly match the lensing expected from an ordinary black hole. These differences are part of what astronomers would hope to find. The challenge is that nature is noisy. Light from distant sources passes through complex regions of space. Dust, gas, magnetic fields, and surrounding matter can all shape what telescopes detect. Even when a strange signal appears, there may be more than one possible explanation. A wormhole would need to stand out not just as unusual, but as more convincing than the many ordinary causes of unusual data. That is a high bar. Astronomy is full of objects that at first seem mysterious and later turn out to be familiar once better data arrives. There is also the problem of distance. The most extreme gravitational objects are often far away, hard to resolve, and surrounded by violent environments. The closer astronomy gets to places where wormholes might hide, the more difficult clean measurement becomes. A compact object near hot gas, intense radiation, and strong gravity is not easy to read like a simple diagram. The signal has to be interpreted carefully. Small uncertainties in the model can lead to large differences in what scientists think they are seeing. Some theorists have proposed other clues as well. A wormhole might influence the motion of nearby matter in a slightly different way from a black hole. It might produce unusual shadows, unusual ringing patterns, or unusual brightness changes under certain conditions. These suggestions are useful because they turn a vague dream into a scientific search strategy. Instead of only asking whether wormholes exist, researchers can ask what measurements might separate one kind of compact object from another. That shift is important. It brings the idea out of pure imagination and into the logic of observation. Still, the search remains difficult because a wormhole may imitate a black hole so well that the difference is hard to tease out. From a great distance, two very different internal structures can sometimes create very similar outside behavior. That means the universe could, in principle, hide wormholes behind familiar shadows. But it also means that extraordinary claims will require extraordinary care. A strange pattern is not enough. The evidence would need to be strong, repeated, and hard to explain any other way. So the sky remains open but quiet. Astronomers know how to search for strong gravity. They know how to track light bending around extreme objects. They know how to compare observations with theory. Yet wormholes have not stepped forward clearly enough to be recognized. For now, they remain possibilities hiding behind the limits of distance, noise, and resemblance. And because the scientific picture is still so uncertain, the human picture becomes even more powerful. Wormholes are not only objects of research, they are also objects of imagination, carried through stories long before any telescope could hope to confirm them. Long before anyone could test wormhole ideas in a modern quantum system, wormholes were already alive in the public imagination. They became part of science fiction because they solved a problem that stories about space always run into. The universe is too large for ordinary travel. If every journey between stars took thousands or millions of years, many stories would simply stop moving. Wormholes offered a beautiful answer. They let writers keep the scale of the cosmos while still allowing characters to cross it. That is one reason wormholes became so popular in fiction. They are not just strange objects. They are story-making devices. A wormhole can connect distant worlds, separate timelines, hidden civilizations, or unknown regions of the universe. It makes the cosmos feel both vast and reachable at the same time. For writers and audiences, that is a powerful combination. The stars remain far away, but not unreachable. Over time, fiction built a very strong visual language around wormholes. They are often shown as glowing portals, shimmering tunnels, circular gateways, or rippling distortions in space. A ship enters one side, strange colors flash around it, and moments later it appears somewhere impossibly distant. The image is simple, memorable, and emotionally satisfying. It turns one of the hardest problems in physics into something the mind can picture in an instant. Some of the most famous examples help shape how millions of people imagine wormholes today. In Contact, the wormhole is treated with unusual seriousness, and the story tries to give the experience a sense of scale and mystery. In Interstellar, the wormhole appears as a real object placed near Saturn, turning a distant galaxy into something suddenly accessible. Other films, television shows, books, and games have used similar ideas for decades. Each version adds another layer to the public image. Together, they have made wormholes feel familiar long before they have ever been observed. Fiction often helps in a real way. It gives people a starting image for a difficult concept. Without those visual stories, the idea of a shortcut through curved spacetime might feel too abstract to hold in the mind. A portal or tunnel is not a perfect description, but it gives shape to the idea. It helps people feel what is at stake. Distance becomes visible. Connection becomes visible. Wonder becomes visible. At the same time, fiction also smooths away many of the difficulties that make wormholes so hard in physics. In stories, wormholes are often stable, easy to find, easy to enter, and surprisingly safe. They behave like roads, doors, or gates. In theory, the picture is much harsher. A wormhole may require exotic stress energy, may be unstable, may collapse under disturbance, and may raise deep problems involving time and causality. Real physics does not give a simple glowing doorway and then step aside. It keeps asking what holds the passage open, what happens when matter enters, and whether the structure can remain consistent at all. This difference matters because fiction can quietly shape expectation. If someone grows up seeing wormholes as polished cosmic shortcuts, it becomes easy to assume that physics is mostly about waiting for better engineering. But the real challenge is deeper than engineering. It is about whether the universe permits these structures in a stable and usable form. Fiction usually begins with the doorway already open. Physics spends most of its time asking whether the doorway can exist at all. Still, science fiction deserves more credit than blame. Many people first become curious about relativity, black holes, and cosmic distance because stories made those ideas feel alive. Fiction does not have to be perfectly accurate to be valuable. Sometimes it teaches by emotion first. It makes the scale of the universe feel real. It makes the dream of crossing it feel worth thinking about. Then science can step in and ask what the dream would actually demand. So wormholes live in two worlds at once. In fiction, they are bridges for adventure, discovery, danger, and awe. In physics, they are severe tests of geometry, energy, and consistency. The gap between those two worlds is large, but it is also fruitful. Fiction keeps the imagination open. Physics keeps the imagination honest. And once both pictures are placed side by side, it becomes easier to ask a calmer question. If wormholes are only one possible answer to cosmic distance, how do they compare with the other ways people have imagined reaching the stars? Wormholes are only one way people have imagined crossing the great distances between stars. They may be the most dramatic idea, but they are not the only one. Once the problem of cosmic distance becomes clear, the mind begins to search in many directions. Some ideas try to make ships faster. Some try to make journeys longer, but survivable. Some try to change the way time is experienced. Wormholes stand apart because they do something different. They do not mainly change the traveler, they change the route. One of the more grounded ideas is the laser sail. In this concept, a tiny probe carries a very light sail, and powerful beams of light push it forward. The probe does not need to carry enormous amounts of fuel because the push comes from outside. This makes the idea attractive for very small spacecraft. A laser sail may, in theory, reach a meaningful fraction of light speed, at least for tiny payloads. But that strength is also its weakness. It works best for small probes, not for large crews, supplies, or entire human journeys. It is a way of sending information and instruments across interstellar space, not a comfortable road for people. Another idea is the generation ship. This is almost the opposite of a wormhole. Instead of crossing the distance quickly, a generation ship accepts the full scale of the journey. a large vessel would travel slowly, and many generations of people would live and die aboard before the destination was reached. This idea does not try to defeat distance. It tries to endure it. That makes it one of the most physically conservative concepts, because it does not require exotic geometry or unknown laws. But it asks for something else that is almost equally difficult: a stable human society sealed inside a moving world for centuries or longer. Suspended animation and similar ideas attempt a softer version of that same solution. Instead of many generations living aboard a ship, perhaps travelers could sleep through the journey or greatly slow their biological activity. This would not make the trip shorter in an outside sense, but it could change how the journey is experienced by the travelers themselves. The difficulty, of course, is that this still leaves the engineering challenge of keeping the ship alive and functioning across immense spans of time. The distance remains. Only the human experience of it changes. Near light speed travel offers another path. If a ship could move very close to the speed of light, the outside universe would still see a long journey, but the travelers might experience less time because of relativity. This makes near light speed travel one of the strangest serious ideas in interstellar thinking. It does not break the laws of physics, but it pushes them to an extreme. The problem is energy. Reaching such speeds would require vast power, protection from collisions with even tiny particles, and engineering far beyond anything humanity can currently manage. It respects ordinary spacetime, but it demands almost impossible performance within it. There are also advanced propulsion ideas that stay within the usual structure of space. These include fusion concepts, antimatter concepts, and other powerful engines imagined for the distant future. Their goal is not to fold space or create hidden shortcuts. Their goal is to move through normal space more effectively than chemical rockets ever could. This makes them easier to picture than wormholes, because they still resemble ships and engines in the familiar sense. But even these bold ideas face steep problems involving fuel, heat, stability, and scale. This is where wormholes become different from nearly every other travel concept. A laser sail is a vehicle. A generation ship is a vehicle. A near light-speed craft is a vehicle. Even the boldest propulsion concepts still imagine a ship crossing the distance between stars, step by step through ordinary space. Wormholes are not really vehicles in that sense. They are more like infrastructure. They are more like bridges, tunnels, or passages built into the fabric of spacetime itself. A wormhole does not ask how to move a ship better. It asks whether the universe can contain a shorter road. That difference is why wormholes remain so captivating. They offer a solution that feels more complete than simply building a better engine. But that same beauty is also what makes them harder. Vehicles ask for energy, materials, and endurance. Wormholes ask for control over geometry itself. They seem less like inventions and more like alterations to the structure of reality. When wormholes are placed beside the other great ideas of interstellar travel, their uniqueness becomes clearer. Some concepts try to survive the distance. Some try to race through it. Wormholes alone try to change the path itself. If a wormhole is not a ship, but a structure, what would it actually take to create, control, and use one? Once wormholes are compared with other space travel ideas, their true strangeness becomes easier to see. A rocket needs fuel. A sail needs light. A generation ship needs life support and time. But a wormhole would need something much deeper. It would need structure. It would need geometry arranged in a way that ordinary space does not seem to provide on its own. That is why the engineering side of wormholes feels so extreme. The challenge is not simply building a craft. The challenge is somehow shaping space-time itself. The first problem would be the most basic one of all. A civilization would need an actual traversable geometry to work with. That could mean finding a naturally existing wormhole, if nature ever produces such things. Or it could mean creating one artificially. Both possibilities are difficult. A natural wormhole has never been observed, so there is no known place to go looking with confidence. An artificial wormhole would be even harder, because it would require creating or manipulating a structure that current physics treats as deeply exotic. Before any traveler could pass through, the passage itself would have to exist. Then comes the throat. This is the narrow region connecting the two mouths, and it would have to remain open against collapse. That alone is one of the greatest challenges in the entire subject. The throat could not behave like a momentary wrinkle that disappears as soon as it forms. It would need stabilization. That may require unusual stress energy, the kind discussed earlier under exotic matter and negative energy. Whatever the exact method, the wormhole could not be left to ordinary gravity. Left unsupported, it would likely pinch shut. So any engineering plan would need a way to hold the geometry open long enough for real use. The mouths would present another challenge. A usable wormhole needs more than an open throat. It needs two ends that are controlled, positioned, and safe to approach. If one mouth opened near a star, intense radiation could make travel dangerous. If one mouth drifted unpredictably, navigation would become almost impossible. If the mouths experienced different motion or different gravitational environments, time effects could complicate the connection in ways that might become useful or deeply hazardous. A civilization trying to use a wormhole would need precise control over where the mouths were, how they moved, and what conditions surrounded them. Safety would matter at every step. The tidal forces inside and near the wormhole would have to remain gentle enough for a traveler, a signal, or a craft to survive. Gravity cannot simply be strong. It must also be smooth enough across the body of the traveler. If one part of a ship is pulled much harder than another, the vehicle could be stretched, damaged, or destroyed. Radiation is another concern. A passage through extreme geometry may not be calm. Fields could fluctuate. Energetic particles might gather. A wormhole used as transportation would need shielding, monitoring, and some way to ensure that crossing it does not become a death sentence. Navigation is easy to overlook, but it may be one of the quietest engineering problems of all. A traveler would need to know where the exit leads, how stable the route is, and whether the connection remains synchronized in a useful way. A tunnel is only useful if it connects the right places. If a wormhole mouth drifts, shifts in time, or behaves unpredictably, then the structure may become less like infrastructure and more like a hazard. Real use would demand maps, controls, and perhaps a whole science of wormhole traffic. All of this makes wormhole engineering feel less like building a machine and more like maintaining a piece of the universe. A bridge across a river is already more than a vehicle. It is a permanent route that changes the landscape around it. A wormhole would be even more than that. It would be a managed feature of space-time itself. It would need creation or discovery, stabilization, placement, shielding, timing, and navigation. The list grows quickly. because the object itself is so unlike anything human engineering has ever touched. That does not make the idea meaningless. In fact, it may be part of what makes the idea powerful. Wormholes force the imagination to rise above engines and begin thinking in terms of geometry, structure, and control over the deepest background of reality. The dream is not simply faster travel. The dream is a universe where distance can be shaped. And once that dream is held long enough, a more personal question begins to appear. If such a passage could ever be made safe and stable, what would it actually feel like to move through it? Once wormholes are imagined as real structures instead of abstract equations, a very human question begins to rise. What would it actually feel like to go through one? The physics cannot answer that with certainty, because no one has ever traveled through a wormhole, and no wormhole has ever been confirmed in nature. Still, theory does give some boundaries. It tells us what would have to be true for the trip to be survivable, and from those limits, we can begin to imagine the experience. The first condition is gentle tidal forces. Gravity does not only pull, it can also stretch and squeeze. If a wormhole had strong differences in gravitational pull from one part of a traveler's body to another, the trip would end instantly. So any safe passage would need curvature that is strong enough to shape spacetime, but smooth enough not to tear apart a person or a spacecraft. That alone changes the image. A usable wormhole would not be a violent whirlpool of destruction. It would have to be a strangely calm road cut through extreme geometry. Visually, the interior might look nothing like a tunnel carved through rock. The familiar word tunnel can be useful, but it may also mislead. A wormhole is a feature of spacetime, not a pipe inside ordinary space. The inside could appear curved, distorted, or difficult for the eyes to interpret. Light entering from different angles might bend in unusual ways. The traveler might see warped stars, shifting brightness, or an exit that looks closer than it should be. The surroundings could feel less like moving through a hallway and more like moving through a place where distance itself has been rearranged. The mouths of the wormhole might be even stranger to look at. From the outside, one mouth could appear like a dark sphere, a distorted window, or an opening into another region of the universe. Instead of showing darkness alone, it might show light from somewhere else. A traveler approaching it might not see emptiness, but another sky. That is one of the most fascinating possibilities in the whole idea. A mouth of a wormhole may not look like an absence. It may look like a presence from far away made suddenly near. The experience of motion may also be unusual. Locally, the traveler might feel almost ordinary movement, as if drifting or flying through a stable passage. From the outside, though, the trip could look astonishingly short. A journey that would normally take years, centuries, or longer through open space might seem to happen in moments. This is one of the deepest emotional features of the wormhole idea. Inside, the traveler may feel a continuous trip. Outside, the universe would describe it as a sudden crossing of enormous distance. Time could add another layer of strangeness. If the two mouths of the wormhole had different histories, perhaps because one moved differently or spent time in a different gravitational environment, then clocks might not agree at both ends. A traveler could experience what feels like a straightforward journey and still emerge into a time that is unexpected. The trip would not only be about where the traveler arrives, but also when. Even without dramatic paradoxes, the simple question of synchronized time may become delicate. There is also the psychological side. Human beings are built to trust ordinary space. A room has walls. A road has length. A horizon stays far away until you approach it. A wormhole would challenge those instincts. The traveler might feel disoriented, not because the ride is physically violent, but because the structure of the place refuses to match everyday expectation. Near and far would behave differently. The exit could seem visible before it feels reachable. The whole experience might create a quiet sense that the universe has changed shape around you. And yet, if the passage were truly engineered for safety, the trip might also feel surprisingly gentle. That is one of the strangest possibilities of all. The most radical journey imaginable might not feel like chaos. It might feel smooth, quiet, and controlled. The real shock would come afterward, when the traveler steps out and realizes that the sky itself has changed. That is what gives wormhole travel its unique mood. It is not only speed, it is not only distance, it is the feeling of moving through a route that should not exist in ordinary intuition. A safe wormhole would be less like being hurled across the cosmos and more like crossing a hidden fold in reality. And once that image becomes vivid enough, the scale of the idea begins to widen again. A single traveler is one thing. A civilization able to use wormholes regularly would live in a universe where distance itself no longer means what it once did. A single wormhole would already change almost everything. It would turn one impossible journey into a reachable one. But the idea grows even larger when imagined at the scale of a civilization. If a society could create, find, or control more than one wormhole, then distance itself would begin to lose its old power. The universe would still be large, but large would no longer mean slow in the same way. A network of wormholes would not simply improve travel, it would change the structure of civilization. Trade would change first. In an ordinary interstellar future, moving goods between stars would likely be slow, expensive, and rare. Whole economies might have to become local because distance would make regular exchange too difficult. But if stable wormholes existed, trade could become something much closer to what roads, ports, and shipping lanes did on Earth. Resources from one star system could move to another without waiting through centuries of travel. A rare material on one world might become common across many. Entire regions of space could begin to function less like isolated islands and more like connected parts of one larger system. Communication would change just as deeply. In a universe without wormholes, even messages are trapped by the speed of light. A conversation between stars becomes impossible in any normal human sense. A reply might take years. A warning might come too late. A culture might drift into complete independence simply because distance prevents ongoing contact. Wormholes would challenge that separation. If information could move through a network quickly enough, then distant worlds might remain part of a shared political, cultural, or scientific conversation. The stars would still be separate places, but no longer separate eras of response. Travel would also take on a new meaning. Without wormholes, a journey between stars is a commitment measured in lifetimes, generations, or extreme engineering. With wormholes, travel could begin to resemble crossing between continents rather than centuries. Exploration, migration, diplomacy, and even tourism would take on entirely new forms. The map of the galaxy would no longer be drawn only by physical distance. It would be drawn by access points. Two worlds hundreds or thousands of light years apart might become close neighbors if a wormhole linked them, while another world only a few light years away could remain harder to reach if no shortcut existed. That is one of the most important shifts in the whole idea. Wormholes would not simply shrink the galaxy evenly, they would reshape it unevenly. The connected places would become central. The unconnected places might remain remote. A wormhole network would create a new geography layered on top of the old one. The true map of civilization would no longer be based only on where things are in space, but on which places are linked by passage. Near and far would become questions of infrastructure, not only of measurement. History itself could change under such a system. A civilization linked by wormholes might stay more unified across time because ideas, laws, and movements could spread more quickly. Or it might become more unstable because rapid connection can also spread conflict, disease, or power struggles. A network that links worlds is never only a path for goods and people. It is also a path for influence. In that sense, wormholes would not just be scientific wonders, they would be civilizational forces. This is also where the silence of the cosmos begins to feel more interesting. If advanced civilizations are possible, and if wormholes can in some way be built or used, then why do we not see obvious signs of such networks? Why do we not observe unmistakable structures, strange traffic, or giant patterns of connected engineering across the sky? There are many possible answers. Wormholes may be impossible in practice. They may be so difficult that only the rarest civilizations ever manage them. They may exist in forms that are hard for distant observers to detect. Or perhaps the universe is quieter than our imagination hopes. Even without a final answer, the thought remains powerful. A wormhole network is more than a transportation system. It is a new way for reality to be organized. It would turn geometry into destiny. It would decide which stars feel close, which cultures remain linked, and which parts of the galaxy live inside the same living web of movement and exchange. That is why wormholes remain so important even before they are proven real. They force the mind to imagine a universe where distance is not abolished, but rewritten. And that leads naturally to one final reflection. Even if wormholes are never built, never found, and never crossed, they still reveal something profound about the universe and about the reach of human thought. So wormholes remain in a very unusual place. They are real in theory, yet unproven in the sky. They emerge from Einstein's vision of curved spacetime, yet quickly run into some of the harshest demands in all of physics. They offer a possible shortcut through distance, yet may also tangle themselves with time, causality, and the deepest limits of reality. The more closely we look at them, the less they resemble a simple doorway, and the more they begin to look like a test of how much the universe can truly allow. And yet, that is part of what makes them so beautiful. Wormholes are not only interesting because they might one day help with space travel. They are interesting because they force us to think differently about space itself. They remind us that distance may not be as simple as it appears. They suggest that geometry can matter as much as motion. They show that the universe is not just filled with objects, but shaped by structures, relationships, and hidden possibilities that human beings are still learning to describe. Maybe wormholes will always remain mathematical dreams. Maybe nature allows them only in fragile, unreachable forms. Or maybe future physics will uncover something deeper that changes the picture again. For now, they remain one of the most fascinating ideas in science because they sit exactly at the edge between wonder and discipline. They invite the mind outward, but they also demand honesty, patience, and care. So when we ask whether wormholes could unlock space travel, the answer is both smaller and larger than it first seems. Smaller because no one has found a usable wormhole, and the obstacles are immense. Larger because the question opens into something deeper than travel alone. It leads into the nature of distance, the flexibility of time, the hidden structure of spacetime, and the strange possibility that the universe contains roots we do not yet know how to read. And maybe that is enough reason to keep looking. Because even if no ship ever passes through a wormhole, the idea has already done something remarkable. It has shown us that once space becomes geometry, the universe becomes far stranger and far more beautiful than a simple emptiness between the stars.